Chapter 16, slides 1 through 5. So I'm going to start with one part of chapter 16, specifically called the Diels-Alder reaction. This is going to be a series of slides where we discuss this one reaction. You might think, wow, that's kind of severe. She's been doing, quick turnaround for each one of the reactions that we cover. Here's a Grignard, right? Here's a reduction. Here's oxidation. We go through the mechanism, done and dusted. Not so much for this one, and there's a couple reasons why I want to slow down on the Diels-Alder reaction. One, the Diels-Alder reaction is an example of a type of reaction called pericyclic reactions. Okay, and pericyclic reactions are concerted reactions dealing with pi systems typically, where the transition state orients itself in a ring, and then in one fell swoop, right, one concerted move, electrons shift and you form new bonds. Now, Diels-Alder is an example, it's one example in this class of reactions called pericyclic reactions. And the reason why I want to spend a little bit more time on it is because this is really one of the first biomimetic pathways that chemists, really got control over. And we're not using enzymes here. So this is, again, shared Nobel Prize back in the 1950s by Kurt Alder and Otto Diels, showing this new reaction. And there's a couple really cool things about it. One of them being biomimetic. What does that mean? It means that this is how nature can form six-membered rings, right? And it means that, showing you this, we can go in the lab and actually do a Diels-Alder in a flask. So this is really cool. The other thing, if you haven't recognized it yet, is that there's a lot of difficulty and challenge in making new carbon-carbon bonds. And so this reaction is one pot and two new carbon-carbon bonds are made. And you'll also notice that you're not really doing it under strongly acidic or strongly basic conditions. Most of the time you just need heat or light. And this makes sense, right? Because if plants are going to use this reaction, that's really all they got. You can't dump chromic acid into the plant to hope it gets to where it needs to go, right? It just needs maybe some heat or light to get this reaction to work. So the Diels-Alder is one example of a pericyclic reaction that represents, for the first time in really this class, a biomimetic method of making a six-membered ring, which we know is nature's magical number, right? Especially in the ring form. So we're going to take a look at this reaction, and you'll notice I've basically simplified it here, and I've made the simplest diene, okay, and I've reacted it with the simplest dienophile, ethene. And what happens, you can see that this is where the bonds are going to form the six-membered ring. So 1, 2, 3, 4. We have this diene, and 5 and 6 are the dienophile. Okay, really this diene is this molecule that has two conjugated in resonance double bonds, and the dienophile is the diene lover. Okay, and what you can see is that when all is said and done, we're going to go over the mechanism in a second, you form this six-membered ring. There still is a double bond given what I started with, but the new bonds are between 1 and 6 and 4 and 5. Now this actual example is not very practical. And we'll discuss why in a minute, but I just want you to know that if I had to actually use this particular this exact diene and this exact ethene dienophile, it would take me about 600 atmospheres of pressure to get these two to react with one another. Now, why might that be? Think about making carbon-carbon bonds, making any bonds really so far in this course. What have you learned about getting a reaction to happen? Right? We talk about our party effect. One of them needs to be partially positive while the other one's full on negative, or vice versa. One of them needs to be full on positive while the other one is partially negative. And that is what's going to get a reaction to occur, right? Well, we saw that even partially positive and partially negatives, most of the time, this didn't even elicit a reaction. So what hope does this reaction even have? I mean, look at the diene. Is there any polarity to it? Is there any part of the diene that's a little bit positive or a little bit negative? No. And look at the dienophile. There's nothing about the dienophile, which is, again, just ethene, that's particularly positive or negative. So this reaction there's no attractive forces bringing the diene to the dienophile to react. You'll need a lot more than heat or light to get this exact reaction moving. That's why it takes 600 atmospheres. Again, we operate under 1 atmosphere. So you need 600 atmospheres to push these two guys and force them together. That's why this particular example isn't really practical. So how do we solve that? Well, we're going to talk about it, but before we do, I want to just go over the arrow pushing of this pericyclic reaction. Okay, so and you might think, oh, this isn't so bad. There's actually a lot going on relative to Diels-Alder reactions, and we'll touch upon a lot of that. As I mentioned, this is the diene, and this is the dienophile. Okay, so I like to number my diene 1, 2, 3, and 4. Find the dienophile, because what you're going to find is that in the Diels-Alder reaction, you'll always end up with a 6-membered ring. Always. So you can almost draw it as your product. 1, 2, 3, 4, 5, 6. However, it's typically not going to be as bare bones as we've drawn it, but let's just focus on the electron pushing. Where are all the electrons going? So the dotted line represents where the new bonds are going to form to give you your reaction. So starting from, a pair of pi electrons. Now, what I want you to recognize here is that only the pi electrons are in motion. None of the sigma bonds, the single bonds, none of those change or break, okay? So pi bond moves here, and for this example, it really does not matter which direction you flow. Pi bond becomes the new 4-5 single bond. Pi bond becomes the new 1-6 single bond. And you can see how it's this cyclic motion of pushing around these pi electrons. Now let's walk through it. Carbon 1 and 2 still have a single bond, but look at 2 and 3. 2 and 3 is gaining a new pi bond. 3 and 4 used to have a pi bond, but now it's using those 2 electrons to make the new sigma bond between 4 and 5. And 5 and 6 used to have a pi bond, but it's now using its electrons to make the single bond between 1 and 6. So walk through it. Here's another example. Your dienophile could be a triple bond. What would that look like? Well, here's my diene, 1, 2, 3, 4. The dienophile just has one extra pi system. I can still use it though. If I add heat or light, let's trace out and practice our, right, those are where the new bonds are going to go. I'm arbitrarily just starting between 1 and 2. I could have started with any of them. And I could have also done it in the other direction. I mean, let's just to show you, I'll start tracing it in the other direction. Let's take this pi system and make the new sigma bond between 1 and 6. Let's use one of the pi bonds between 5 and 6 and make the new bond between 4 and 5. Let's use the pi bond between 3 and 4 and come full circle, making a new pi bond between 2 and 3. Let's draw the result. And as I mentioned, you're always going to get a 6-membered ring, so you can very easily trace that out and fill in the details after. So the new bond between 1 and 6, the new bond between 4 and 5, if you'll notice, when I lost the 3-4 pi bond, I now have a new bond between 2 and 3. You'll also notice that 5 and 6 only used one of its pi bonds, and so there remains a sigma and another pi. So the answer here looks like this. Okay. So now with understanding where the electrons are moving and motioning through, let's understand how this works relative to heat and light. I also want to answer the question I posed at the bottom. So how do we get the reaction to work and not have 600 atmospheres? Okay, so what we're going to do is we're going to use inductive and resonance effects. Okay, so what we're going to do is we're going to take a diene, and we're going to take a diene and we're going to place an electron donating group as one of the appendages off the diene. Okay, so if you think about it, an electron donating group, right, this guy, is going to make the diene electron rich. It's going to donate electron density to the diene. If I do that, what do you think we should put on the dienophyte? If you've guessed the electron withdrawing group, then you'd be right, because an electron withdrawing group is going to make the dienophyte electron poor. Now, electronically, there's a reason for these two to come together. You have an electron-rich diene and an electron-poor dienophyte. They will come together. We'll talk more about what these look like, but I want to map out how this orbital theory works for you guys. Seeing the orbital theory will also help you to understand why these work under just light or heat. And also, it's the basic theory around a lot of pericyclic reactions, when things can occur and when things are not allowed. All right, so carbons 1, 2, 3, and 4. You would agree, right? 1, 2, 3, and 4. I've just drawn it out. This is the same as this. These are the same, okay? These are equal. And if I represent 1 and 2 and 3 and 4, you'll recognize as well that if I just draw them out as p orbitals, right? They're double bond here, but because they're right next to each other, there's resonance, and really they're all in conjugation, talking with one another. We're going to talk more about conjugation in part 2, but I just want to show you that this is another way to draw carbons 1, 2, 3, and 4 using p orbitals. I'm not going to draw the orbitals for the sigma bonds, because they're actually, if you remember from the electron pushing, the sigma orbitals, the sigma bonds, are not in play here. When we pushed electrons, the only electrons that are in motion came from the p orbitals, right? From the pi bonds. The sigma bonds don't really play a role in here. So we're just going to map out the orbitals. This is called frontier molecular orbital theory because we're only using the orbitals and the electrons and the orbitals at the frontier of the reaction, right? It's like kind of the war zone. It's the front line. It's really not what's going on towards the back. It's who's in action, what's happening right there and at the forefront. So understand that orbitals are wave functions, right? Because they're wave functions, they have wave-like properties. They have in-phase and out-of-phase bonding and anti-bonding nodes. So the lowest energy of the diene, okay, has all of the p orbitals in phase. Now, a node, right, is in these wave functions, right, just like when you have, if you had a wave function, right, a node is at that 0 mark. It's where the phase changes, okay? So there is only one node going right through here. This is our node, okay? So there's one node, because the phase change for all of them goes from top to bottom. Now, as you increase nodes, you get higher in energy. Okay, so there's only one node here. So the next energy is where these orbitals, phase-wise, have two nodes. Now they have two nodes, right? One going through the middle, and now there's a node because as you compare from left to right, there's a change in the phase. So there's a nodal change. So there's two nodes in the second one. So one node, two nodes. The next highest energy of these wave function orbitals would be three nodes. How do we do that? Well, we're going to color one of them like this. So again, you can see that there's a node that runs all the way through. If you compare what's on the top to the bottom, there's a node. It's a node because the wave function phase changes. There's also a node here, because when you compare left to right, there's a change. And there's a node here, left to right. So that has three nodes. Four nodes. You can imagine what this one is. This was the easiest one. I always think the third one is the toughest to conjure up. And this is basically all of them alternating. Four nodes, right? We've got one through the center, 2, 3, 4. Between every orbital, you see one. Okay, so these represent from lowest energy to higher energy the different wave function orientations of this conjugated diene. So each one of them has an energy level. Now, how many electrons are in the pi orbitals? Okay, how many electrons are in those p orbitals? Well, you've got the electrons between 1 and 2 if they were stagnant, the electrons between 3 and 4, right, in the p orbitals, the pi system that are stagnant, if they were stagnant, but they're not. So there's really 4 electrons in play here. So we're going to fill from lowest energy up 1 electron, 2, 3, 4. Okay, so orbitally, when we're trying to figure out whether these reactions are allowed and how well they're going to run, this is what I want to draw up for the diene. what you'll notice is that this guy right here is called the HOMO. HOMO stands for highest occupied molecular orbital. It is the highest orbital we've got that is filled, right? It's the highest occupied with electrons molecular orbital. So this one is, the HOMO. Right above it is what we call the LUMO. The LUMO is the lowest unoccupied molecular orbital. So this guy is the LUMO. Okay, that's the diene. Now what we're going to do is we're going to look at our dienophile. Now I'm just going to draw out the simplest one again. We're assuming that our diene has an electron withdrawing group on it and the dienophile has an electron withdrawing group on it. Okay, so if I were to say, you know, this represents the diene with the electron donating group, what I'm going to draw next is the dienophile with the electron withdrawing group on it. So we're going to start right around here. How do I know where to start? Well, I know because of experimental data, but for you, you're just kind of following along and trusting that I know where the energies are. So there's only carbon 5 and 6, right? So there's only 2 carbons and they have 1 pi bond between them. So we're going to represent the dienophile, the 2 carbons, 5 and 6, with its pi bond, but we're going to use the orbitals. And the lowest energy orbital system with the wave function phases is going to be in phase with 1 node. Okay? And then there's only one other way to draw this, and that's with 2 nodes out of phase. I mean, because we only have 2 p orbitals to deal with, this is the only other one I can draw. How many electrons are involved in this 5-6 pi system? Well, 2. So we're going to fill from lowest energy and up. So this one is the HOMO, and this one is the LUMO. Now, what happens is that the HOMO of one will interact with the LUMO of the other. And you can see that you could go LUMO to HOMO in this direction, or you could go HOMO to LUMO in this direction. Whichever one has the smallest energy difference is the one that is used. Okay? So what we're going to do is we're going to take each of these and make new molecular orbitals so that we can do this Diels-Alder reaction. So we're going to react the HOMO and the LUMO, a filled with an unfilled. And when you look at the phases, okay, you want to see if the phases align so that the reaction is allowed. If the phases don't align, then this HOMO-LUMO combo can never work. We're going to have to do something different. So what does this mean? So I want you to take a look at this 2-node phase diagram and alternating dienophile phase diagram. Those are the 2 systems those are how the orbitals are going to have to be when they interact. So you'll notice you can see the node going through and then the node right in between. This is the HOMO. You can go back and check for yourself. The HOMO of the diene. And this is the LUMO of the dienophile. Now what you'll notice is that when you use the HOMO and the LUMO of the diene and the dienophile, the phases align. Look at the phases on the ends. All right, if this is carbon 1, 2, 3, 4, 5, and 6, you'll notice that 1 and 4 have opposing phases, which is good because we're going to be reacting those 2 carbons with the 5, 6 of the dienophile, and they too are out of phase because we're using its LUMO. Notice that white goes to white and dark goes to dark. That means the phases are aligned with one another. And so I also want you to notice that what's happening is that you're not bringing them side to side, right? Remember, that's not what's happening. What's happening is that you're bringing a pi system, you're stacking it. Because when these two come together, they are going to make a sigma bond. Remember, these are sigma bonds. Those are head-on overlaps. So look at the orientation of how it stacks. They're not coming in side by side. They're stacking on top of each other. And what you'll notice is that the transition state, as the diene is, cupped or like shaped like a mouth, understand that the dienophile comes in from below. I have it shown coming in from the bottom. I could have had it come in from the top, but this is showing a bottom face attack. Okay, so the LUMO is coming in from the bottom. You could also imagine, I could have drawn it coming in from the top. And so all I've done is I've just taken this transition state model with the dotted lines showing where the new bonds are, rotating it to show you that really the transition state for a Diels-Alder reaction sets itself up using the boat configuration, not the chair. This is a boat six-membered ring transition state, not a chair, which is actually better, but it just can't get into a chair if it wants to react with the orbitals. If the orbitals need to align and overlap to make the new bonds, the chair doesn't get you there. You need to have it in a boat configuration.